Now that we've learned some of the fundamental concepts of differential equations, it's time to consider some applications of this important area of mathematics. Differential equations are used everywhere across the sciences in engineering, chemistry, physics, biology, electronics, you name it, there's differential equations all over the place. Many very important, very significant problems can be phrased as differential equations. So knowing how to set up and solve differential equations is an incredibly powerful tool in the real world. We'll just look at 3 real-life applications of differential equations here, and some of these we'll study more in depth later. First of all, let's consider the natural growth model. We're thinking here of a population. This could be a population of insects, it could be a population of bacteria, whatever we want really. But let's suppose that a population, which we'll call P, and this is a function of time. The T here is the time variable. So we're thinking of population changing over time. Let's suppose that the population grows at a rate, and here dp dt, we want to think of that as the rate of change of the population. So suppose that a population grows at a rate that is proportional to the current size of the population. We want to set up a differential equation that describes this growth model. Now before we do that, let's talk a little bit about the derivative here and how to think about dp dt. dp dt is the derivative of population with respect to time. Time is the independent variable, population is the dependent variable. We want to think of dp dt as the rate of change of population. And for these applied problems, that's really the best way to think about the derivative. So we could call this p prime if we wanted, but in any case, we want to think of this as the rate of change of the population with respect to time. So thinking of derivatives in this physical sense here is very important for these applied problems. So this natural growth model says that the rate of change of population is proportional to the current population size. And if we think about this for a second, this could kind of make sense. Imagine having a population, let's just say of rabbits. Let's imagine that we have some number of rabbits. Basically what this says is that the more rabbits we have, the faster the population grows. The rate of change is proportional to the current size. So if we have a small current population, the growth rate is small. There's not that many rabbits being born. If we have a large population of rabbits, then the growth rate is also very large. The growth rate is proportional to the current size. Now, how can we set up a differential equation to describe that? Well, the answer is to take the derivative, dp dt, that is the growth rate, and we're told that that's proportional to the current size of the population. The current size of the population is P, just whatever the population is. We could call this P of T, or we could just call this just P. So if the growth rate is proportional to the current size, that means that the growth rate is some multiple of the current size. That's what this equation says. It says that the growth rate, the derivative, is proportional to the current size P of the population. This expression here is called the natural growth model. This describes population growth as being proportional to the current size. And again, to phrase it more simply, this is just saying that the larger the population is, the faster the population is growing. This is called the natural growth model, and we'll solve this in a future section. Let's talk now about the logistic growth model. Once again, we have some population, and initially, we're imagining that the population grows at a rate that's proportional to the current size. So initially, we have natural growth for this population. However, we're going to imagine here for the logistic growth model that there is some upper limit on what the environment can handle. We're going to suppose that the growth rate slows down as the population approaches some size limit. We'll call that M, and the name for this size limit is the carrying capacity. So imagine here again that we've got some population of rabbits, but now the rabbits are on an island, and the island is in the middle of the sea, and this island only has a finite number of resources on it. So imagine here that we have enough room for, say, 100 rabbits. 100 would be the carrying capacity of this population. So we have a population, and initially, if the population is small, it doesn't feel the effects of the environment. It's not restricted by the size of the island. When we have just a few rabbits, they can roam around however much they want, and so we have natural growth with a small population. So initially, growth rate is proportional to the current size. But as we get more and more rabbits, as we get, say, 70, 80, 90, as we get more and more rabbits, they start to feel the effects of the environment. They can't populate this island anymore because they're taking up all the space. So the growth rate will slow down as the population approaches the carrying capacity, which we use the variable m for. Now, how can we describe this behavior mathematically? Well, what happens if the population is small? If the population is small, then the growth rate is proportional to the current size. So if the population is small, this derivative is just k times p. We have natural growth for a small population. As the population continues to grow, it starts to approach this carrying capacity m. So what happens when the population is roughly equal to m? Well, if the population is really close to m, then the growth rate is basically 0. So the derivative would be 0. That means that the population is not growing when the population is close to this carrying capacity. Now, imagine that we have a ship carrying 50 more rabbits, and the ship unfortunately sinks close to the island, and all the 50 rabbits swim to shore, and now we have 150 rabbits on the island, or close to 150. Well, that's a problem because the island can only support 100 rabbits. So we have a population greater than the carrying capacity. If the population is greater than the carrying capacity, that means the growth rate is negative. In other words, we're losing bunnies. So it's bye-bye bunnies. So these concepts here are describing this logistic growth model. At first, the rabbits don't feel the size constraint of the island, so we just have natural growth. But as we get more and more rabbits, the population growth slows because they're starting to approach the upper limit or the carrying capacity of what the island can support. But how can we take all of these little pieces of information and compile them together into one single differential equation? Well, here's what that single differential equation is. dp dt, that's the growth rate, is proportional to the population, but then we're going to multiply by a factor here to correct for the carrying capacity. We'll multiply by 1 minus p over m. And let's just imagine what happens here for these different scenarios. If p is small, then this fraction here, we have a small number over m. M is a constant. In this case, we're thinking of 100. So we have a small number over 100. This fraction would basically be 0. So if p is small, if the population is small, then p over m is approximately just 0. So that'd be 0, and we have 1 minus 0. So inside the parentheses here, we just have 1. So we multiply 1 by kp. In that case, we get rate of change approximately equal to kp. Now, what happens if the population is roughly equal to m? If the population is roughly equal to m, then this fraction, p over m, I have essentially m over m. So that fraction turns into basically 1. So p over m is essentially 1. And then inside the parentheses here, 1 minus 1, I have a 0. So in that case, kp times 0, this growth rate is approximately 0. Now, if the derivative, or if the population rather, is greater than m, then this fraction would be greater than 1, and we'd have 1 minus something greater than 1. I would have some negative quantity inside the parentheses. Negative times kp, that's negative. So if the population is greater than the carrying capacity, then we have a negative growth rate. That just means that the population is declining. So this differential equation is encapsulating all of these ideas here for the logistic growth model. Let's switch gears from populations and let's talk about Newton's law of heating and cooling. So Newton's law of heating and cooling states that the rate, and when we see this word rate, we want to think derivative. This is where we get the derivative for the differential equation. The rate at which the temperature of an object changes is directly proportional to the difference between the temperature of the object and the temperature of its surroundings. So we're going to describe this situation using a differential equation. And before we describe this, let's try to understand exactly what Newton's law of heating and cooling is saying intuitively. Imagine that you have a freshly brewed cup of coffee that's just about boiling point, 212 degrees Fahrenheit. And imagine that you have that in a normal room temperature room, about 70 degrees. That coffee will start to cool. But now think of what would happen if you took the coffee and instead of having it just in the room, put it in a freezer. If you put it in a freezer, it's going to cool a lot faster. And the reason is because you have a greater temperature difference when the coffee's in the freezer. So when you have a larger difference between the temperature of the object and the temperature of its surroundings, you'll have a faster rate of change of temperature. That's all this is saying. If you take coffee and have it at room temperature, it won't cool as fast as if you put it in the freezer. Essentially, that's what Newton's law of heating and cooling says in a nutshell. How can we describe this using a differential equation? Well, we first want to fix some variable names. So we're going to let H be the temperature of the object. So H, think of this maybe as heat. We've got a hot cup of coffee. H is the temperature of that cup of coffee. And the temperature of the object at any time after T equals 0. And then we're going to say capital T is the constant temperature of the surroundings. Maybe this is room temperature, or maybe it's the temperature of the freezer, but this is going to be a constant temperature. This will not change as we cool down the object. So let's pick apart this statement and let's just add in some expressions here. So rate at which the temperature of an object changes. This is talking about a derivative, and this is the derivative of the temperature of the object. So again, rate here we want to think a derivative. So this is talking about the derivative of h. We could call it h prime, or we could call it dh dt. dh dt is the rate at which the temperature of the object changes. And it's really important that we are really comfortable with this expression for the rate at which the temperature of an object changes. The derivative tells us the rate of change. That's the rate at which the temperature changes. All right, so this is directly proportional to, now let's talk about this next part, the difference between the temperature of the object and the temperature of its surroundings. Okay, the temperature of the surroundings, we're calling that T. So temperature of the surroundings is T. Temperature of the object, that's what we're calling H. So the difference between these, this is going to be H minus T. That's the difference between the temperature of the object and the temperature of the surroundings. Newton's law of heating and cooling says that this rate is proportional to this difference. We can write that in a single equation. We can say the rate, dh dt, is proportional to the difference. So it's some multiple of the difference h minus t. Here is the differential equation that describes Newton's law of heating and cooling. And I highly encourage you, if this is still a little bit confusing, rewind and watch this part of the video again. Make sure that you're comfortable with this notion that we can describe a physical phenomenon like the cooling or heating of a coffee cup. We can describe it very effectively using a differential equation. In a future section, we will solve this differential equation, and that will give us a function to model the temperature at any point in time. So here we have 3 different scenarios that we can model using differential equations. Notice for each one of these, the independent variable is t. Usually we've been using x instead of t, but t is time here. That's our independent variable. And notice that none of the differential equations directly depend on lowercase t. This one has the capital T, but that's temperature. Each one of these differential equations is just a function of the y. So here we have derivative equal to some multiple of y or p here. Once again here there's no time variable t that directly shows up. And again for Newton's law of heating and cooling, there's no lowercase t for time. What do we call this when we have differential equations that only depend on the dependent variable on the y? These are called autonomous. So each one of these important applications is an example of an autonomous differential equation. Let's take a look now at one final example for this section. Take a look at problem 6. Here we have a differential equation. It is a first-order differential equation. It's not autonomous because it depends on x. And we want to show that the general solution is this right here. Now, where does this general solution come from? How do we come up with that? Don't worry about that for now. We don't need to know the method. In fact, for this particular example, we're not going to really see a method that would work to solve this. So we won't worry about developing this solution, but we will show why this function satisfies the differential equation. So our differential equation is x squared y prime equals 1 minus xy. And we want to show that the following function is the solution. It is y equals natural log of x plus c divided by x. So we need to find the first derivative here. So we'll take the first derivative to find y prime. This is going to require the quotient rule because we have a fraction. So y prime, quotient rule says take the derivative of the numerator, 1 over x, times the denominator, minus the numerator, times the derivative of the denominator, which is just 1, all divided by the denominator quantity squared. So using quotient rule, there's the derivative of our original function. When we have 1 over x times x, those just cancel to get 1. So in the numerator here, we'll have 1 minus natural log of x minus c divided by x squared. That is y prime. Now that we've got y prime, we're going to separately analyze the left-hand and right-hand sides, and we're going to show that these simplify to be the same thing. Once again, I don't want to just write the left-hand side and then write the right-hand side and put them both equal to each other right away, because I'm then assuming that they're equal before I've verified it. I want to work separately here. So first, we look at the left-hand side. Left-hand side of the differential equation is x squared y prime. So x squared and then y prime we just solved. This is that rational function, or not rational function, it's that function there. So 1 minus natural log x minus c divided by x squared. We can do some simplifying here. The x squareds will cancel, and we are left with just the numerator, 1 minus the natural log of x minus c. Now let's focus on the right-hand side of the differential equation. Right-hand side of the differential equation is 1 minus xy. And y is this expression here. So we have 1 minus x times y, which is natural log of x, plus c over x. I'm just taking this expression for y and plugging it in here. Simplify this now. The x's will cancel. So we have 1 minus natural log of x minus plus c, so minus c. And notice these left and right hand sides are equal. So we have verified that this function is the general solution to this differential equation. The next part of the problem is to graph several specific solutions on the same coordinate axes. So we'll go ahead and plot our general solution. We have natural log of x plus c divided by x, and we'll add a slider value in for c. All of these different curves are different particular solutions to the differential equation. And again, we'd like to graph the differential equation, but we can't really graph differential equations in the normal sense that we're used to graphing things. If we try to put this in here, x squared times y prime equals 1 minus xy, we don't get anything meaningful here. We can't just plot derivatives like this in the normal way that we plot functions. So we have this family of solutions. Let's look at a whole bunch of these at once. We can modify c here to range from a certain set of values. Let's go from -5 to +5. Look at that. All of those different curves are different valid solutions to the initial differential equation. So all of these are solutions to the differential equation. We have a family of solutions here depending on what value we choose for that constant c. So now that we've visualized many specific solutions for this differential equation, let's solve part C. We want to find solutions with the following initial values. So we are solving two initial value problems. We have a differential equation with an initial condition. This is called an initial value problem, and we've got two of them here. So we're going to take the general solution. We will use these points for the x and y values, and we will find two specific solutions for these two different scenarios. So for part C, let's look at the first one. We have the initial condition, y of 1 equals 2. This is the same as saying that the point 1, 2 is on the solution curve. These are x and y values. So how do we find this specific solution? We take the general solution and we plug in 1 for x, 2 for y. So the general solution, we'll just write it right here. General solution is y equals natural log of x plus c over x. There's the general solution, and we are going to plug in these specific values for x and y to solve for c. So y equals 2, x equals 1. Natural log of 1 is 0, and then we're dividing by 1, so we can just ignore that 1 in the denominator. So we just get c. c equals 2. So we take our original general solution and replace the c with 2. So the specific solution here is y equals natural log of x plus 2 divided by x. That's the solution for this initial value problem. Now for the second initial value problem, for part 2 here, we have a different initial condition. Here, the initial condition is y of e equals negative 1. So now we replace the x with e, replace y with negative 1. We start with the same general solution, but now y equals negative 1, and we have e instead of x. And we'll solve for c. So multiply both sides by e. We'll have negative e equals the natural log of e. The natural log of e is just 1 plus c. This tells us that c equals negative e minus 1. There's the value for c. So now the specific solution here, we replace the c with negative e minus 1. So natural log of x minus e minus 1 over x. Here's the specific solution for the second initial condition. So we'll take a look at these in Desmos now, and we'll see that this first specific solution passes through the point 1, 2. The second particular solution passes through the point e negative 1. So here in Desmos, once again, here's our family of solutions. This is the general solution with different values for c, but we want to plot the two particular solutions that we just found. So the first one, the c value was 2, and this is supposed to pass through the point 1, 2. There it is. So there's the particular solution satisfying this initial condition or passing through that point 1, 2. The second one, the c value was minus e minus 1. So minus e minus 1, and this should pass through the point e, negative 1, which indeed it does. So there we have two particular solutions that we found that satisfy these initial conditions that we were given. And this, once again, is called an initial value problem, finding the solution to a differential equation that satisfies some initial condition.